In this problem, we are asked to derive the differential equation of motion for the single degree of freedom system that we see here on the screen. The system is made up of a particle mass P, which is attached to a massless rigid bar OP, with O being pinned to ground there at the top. It's hanging in a vertical plane. We're going to describe the position in terms of the angle of theta, and we're going to use the Lagrangian approach to derive our equation of motion. So the first thing we need to do, of course, is to draw an FBD of our system. So what I will do is I will draw an FBD of the rigid body, the rigid bar with the particle attached. And the forces that we have acting on this are going to be the reaction forces of OY and OX acting at point O. Of course, it's going to be the weight force of mg, and that's it. We know in terms of deriving the expression for the differential or the virtual work that these two forces won't make a contribution. They act at a point that doesn't move. Although the weight force will be doing work, we're going to include that work through our potential term of U. So, the differential work, the conclusion from that, is a 0. So therefore, our generalized force of Q theta is a 0. Kinetic energy expression T is 1/2 mv squared, where v is for the particle P. And from kinematics, we know that the speed of P is equal to L times theta dot. So therefore, this becomes 1/2 mL squared theta dot squared. The potential energy expression that I'm going to write down will be based on a datum line that I'm going to draw passing through point O. So the potential for this is going to be mgl cosine. And since theta in the range that we're looking at here puts the pendulum below that, we need to have a negative sign there. So again, comes back to how I define my datum line. The negative sign I have here is that because it falls below there. So from that, we can write down our different terms that are coming into play for the Lagrangian expression. We get time derivative of the partial t with respect to theta dot. So this is 1/2 mL squared 2 theta dot, like this. 2's cancel out, of course, and this becomes mL squared theta double dot. When we look at partial t with respect to the angle theta, there is no dependence. We look at how U potential changes with the angle of theta. We get minus mgl minus sine theta. So the minus and a minus, we get a plus mgl sine theta. So therefore, Lagrange's equation, the ddt of partial kinetic energy with respect to theta dot minus partial t with respect to the angle of theta, partial u with respect to the angle is equal to q theta. We saw that these two terms are gone. And so therefore our Lagrangian formulation gives us the following differential equation. mL squared theta double dot plus mgl sine theta is a 0. We might go through and divide by that and get theta double dot plus g over L sine theta is a 0. So this is what the Lagrangian approach gives. If we use Newton's second law, we of course would end up with the same equation with really out much more difficulty. This is more of an example to show how the method works, not to demonstrate that it's better or worse approach than a Newton. Also, the simple pendulum is a typical model that we oftentimes use for single degree of freedom systems, where the system has rotational coordinates. And so by putting it in the form that I have, then what we can say is that when theta is small, it says sine theta is approximately the angle itself. We get theta double dot plus g over L. Theta is a 0. And later on we'll see in the course that we can recognize this as being the square of the natural frequency. In other words, the natural frequency here in this case would correspond to small oscillations, and that would be the frequency at which it would freely swing given a set of initial conditions. We'll get into that later on in the course.